Hello everyone, welcome back to the Atharva Academy. Myself Chinmay Dhaduk. Now in this video we are going to start chapter 9, that is pressure vessels. Now what is pressure vessels? It is one type of container which is used to store fluids under pressure. Here you can take example of boiler. In the boiler we know that we store fluid which is under high pressure, and that boiler is also called as pressure vessel. So in this chapter we will discuss types of pressure vessels, then we will discuss stresses and strain in the pressure vessels, and we will also see that how to design these pressure vessels. Means we will understand that how to find thickness or diameter of these pressure vessels. Fine? Now basically there are two shapes of pressure vessels. One is cylindrical and second is spherical. In cylindrical, pressure vessels have shape of cylinder, means it is like this, and the spherical pressure vessel have shape of sphere. And there are also other two types of pressure vessels. One is thin pressure vessel and second is thick pressure vessel. Now let's say T is the thickness of this pressure vessel and D is the inner diameter of this pressure vessel. So if this thickness of pressure vessel is less than diameter by 20, then we can say that this pressure vessel is thin pressure vessel. And if the thickness of pressure vessel is greater than or equal to D by 20, then the pressure vessel is called as thick pressure vessel. So actually here we can say that diameter by thickness is greater than 20, right? And here we can say that diameter by thickness is less than or equal to 20. Fine? So actually this classification of pressure vessels is based on the ratio of inner diameter of pressure vessel to the thickness of pressure vessel. Fine? Now in the syllabus of strength of material there is only thin pressure vessel. So in this chapter we are only going to focus on thin pressure vessel. Means we will only discuss thin pressure vessels in this chapter. Fine? Now we are going to discuss stress in cylindrical pressure vessel. Now here in the figure you can see that we have this pressure vessel which is cylindrical in shape. Here actually these both ends are closed, but it may be open at one end. Means if it is vertical cylindrical pressure vessel, then upper end of cylindrical pressure vessel may be open. Fine? Here this is the inner diameter of this pressure vessel. Let's say it is small d, and this is the thickness of pressure vessel, that is small t. Now here we are assuming that thickness of this pressure vessel is less than diameter by 20. Means here we are assuming that the cylindrical pressure vessel is thin pressure vessel. Fine? Let's say if we view from this side, then we will get front view of the cylindrical pressure vessel like this. It is like this. And here I have shown the side view of this cylindrical pressure vessel. So this is the front view and this is side view. Now if we store fluid in this pressure vessel, let's say having pressure P, then we will get pressure on inside wall of this pressure vessel, and it will be like this. Here this pressure is always perpendicular to the surface. Fine? And here we will also get pressure like this. And on this surface also there will be pressure. Here pressure on the side wall is also shown here. Fine? Let's say here length of this pressure vessel is small l. So we can say that this axis is axis along length of this pressure vessel. So we can say that it is longitudinal axis. And here this direction is radial direction, right? And here this is the circumference of the cylindrical pressure vessel. So we can say that this direction is the circumferential direction, or we can also say that it is tangential direction to this cylindrical pressure vessel. Fine. So now due to this internal pressure P, there will be stresses in all the three directions. One will be in longitudinal direction, second will be in circumferential direction, or we can say in tangential direction, and third will be in radial direction. Means here we will get three type of stresses. So here we get these three stresses in three direction, and stress in longitudinal direction is called as longitudinal stress. Stress in circumferential direction is called as circumferential stress, or it is also called as tangential stress or hoop stress, and stress in radial direction is called as radial stress. Now in the case of thin cylinder, value of radial stress is very less than other two stresses. Means it is less than longitudinal stress, or we can say circumferential stress, or it may be also called as hoop stress. Fine. So actually in the analysis of thin pressure vessel, we neglect value of radial stress. Means we assume that radial stress is negligible. Fine. So here we will only consider stress in longitudinal direction and stress in circumferential direction. Now let's say here we take cross section of the cylindrical pressure vessel in this direction. So it can be shown like this. Fine. Now here we know that there is pressure acting in this direction. So there will be stress on these both surface, which will be in this direction, and it is in the direction of longitudinal axis. So we can say that these stresses are longitudinal stresses. Means here we can say that longitudinal stress is the stress in the direction of longitudinal axis of cylinder. So here this is the stress which is longitudinal stress. Now here we know that this cylinder is in the equilibrium. So we can say that sum of forces in longitudinal direction is equal to 0. And here two type of forces acting on this pressure vessel. One is due to this pressure P, and second is due to this stress. Now what will be the value of force by this pressure? It will be P into A. And here this is the area on which this pressure is acting. Means it is this circular area. Fine. So this area is pi by 4 d square. And what will be the value of force by this longitudinal stress? It will be sigma L into area. And in this case, what will be the value of area? Here this stress is acting on this surface. So here we have to take this area. Fine. So this area will be pi into d into t. Here this pi d is the perimeter of this circle and t is the thickness of this pressure vessel. Fine. So now we have to equate both these terms. So it will be p into pi by 4 d square is equal to sigma L into pi d t. Here this pi is cancelled. Here this 1d will be cancelled. So finally you will get sigma L is equal to Pd by 4t. Here this P is the value of pressure acting on the cylindrical pressure vessel. This d is the inner diameter of the cylindrical pressure vessel, and this t is the thickness of this cylindrical pressure vessel. Fine. So if it is asked to find out value of longitudinal strain in the body, then you can use this equation. So you have to remember this equation and mark this equation as a important. Fine. Now we are going to discuss hoop stress. It is the stress in the circumferential direction of cylinder. Means in this cylindrical pressure vessel, stress in tangential direction is called as hoop stress, and this stress is also called as tangential stress or circumferential stress. Fine. Now if we take cross section of this cylinder at any diametral direction like this, then we will get this type of cylindrical pressure vessel. And on this cylinder there is pressure on these side walls, and here there will be stresses on this surface like this, and here these stresses are hoop stress, and here this is the pressure, that is P. Now here, due to this pressure on the inner surface of this cylinder, there will be force in this direction, and due to these stresses there will be force on this part of cylinder in upward direction. Fine. So actually this part of cylinder is in the equilibrium, so we can say that sum of forces in vertical direction is equal to 0. So in this case, force due to these stresses and force due to this pressure will be same. Now here you have to remember that for any curved surface, pressure force is mathematically force on projected area. Means here force due to this pressure will be P into A, and here this area will be taken as projected area of this curved surface. Means we have to take this area. Right, because this area will be projected area by this curved surface. Fine. Forces by this stress, we have to take sigma h into area, and in this case this area will be this area on which stress is acting. Fine. So here we have to equate this both the forces. This force by stresses is sigma h into area. Now here what will be this area? Here we know that this is the length of this cylinder, that is L, and this is the thickness of this cylinder. So here this area will be 2T into length, and it is equal to pressure into this projected area, that is D into L. Right, here this is the diameter of this pressure vessel, and here this L is cancelled from both the side, so we can find sigma h is equal to PD by 2T. So this is the stress along circumferential direction of this cylindrical pressure vessel, or we can also say that this hoop stress is along the tangential direction of this cylindrical pressure vessel. Fine. We have discussed that longitudinal stress is equal to PD by 4T and hoop stress is equal to PD by 2T. So from here you can see that value of hoop stress is equal to 2 times value of longitudinal stress. Means in the cylindrical pressure vessel, value of stress in tangential direction is double than stress in longitudinal direction. So always cylindrical pressure vessels is going to be failed by hoop stress. Fine. So if we consider that this is the front view of cylindrical pressure vessel, then we can assume that the cylindrical pressure vessel is going to be failed from here, or it may be failed from here. Means it will fail due to this hoop stress sigma h. Fine. Let's say in the question, if efficiency is given to you along longitudinal direction, then you have to take this eta L here, So your equation will become sigma L is equal to PD by 4T into eta L. And here this is the efficiency. Here this efficiency is efficiency due to non-homogeneity of material, or it may be efficiency due to joint in longitudinal direction. And similarly, if efficiency is given for hoop stress, let's say that is eta H, then you have to put eta H here, and this will be the equation to find out hoop stress in the body. Fine. Now we have also discussed that in the radial direction there is stress which is called as radial stress sigma R. So generally for thick cylinder, value of the sigma R is minus P. Means here if pressure is P, then stress in radial direction will be compressive in nature, and that will be having value minus P. But we have discussed that for thin cylinder, value of this radial stress is very less, so actually we neglect the value of radial stress in the analysis of thin pressure vessel. And here in the analysis of this cylindrical pressure vessel, we also neglect weight of this pressure vessel. Fine. Now let's say we take any small point or small cube from the surface of this body like this. So here there will be longitudinal stress in this direction, that is sigma L. There will be circumferential stress in this direction, there will be sigma H, and there will be radial stress in this direction, that is sigma R. And this is the state of stress shown here on this cube. Here in this direction we have this stress sigma L, that is having value PD by 40. This is the hoop stress, that is having value PD by 2T, and this is radial stress, that is having value minus P. And as we know that for thin cylinder we neglect this radial stress. So actually we have this case which is of 2D loading condition on the body. Fine. Now understand that on this plane there is only normal stress acting. There is no any shear stress on this plane. So we can say that this plane is principal plane, right? Because principal plane is the plane on which there is no shear stress acting. That we have discussed in the chapter 7. Fine. So in this case, this longitudinal stress will be the principal stress. And similarly on this plane, there is only normal stress is acting. There is no any shear stress on this plane. So we can also say that this plane is principal plane, and stress on the principal plane is called as principal stress. So here this sigma H is also principal stress. We know that sigma H is equal to 2 times sigma L, means sigma H is greater than sigma L. So in our case we will take this sigma H, means this hoop stress, as maximum principal stress, and this longitudinal stress as minimum principal stress. Fine. We can also represent this state of stress in 2D loading condition here. Here in this direction we will take hoop stress, and in this direction we will take longitudinal strain. So actually in this direction there is hoop stress, and in this direction there is longitudinal stress. Fine. Now here we know that sigma 1 is equal to sigma H and sigma 2 is equal to sigma L. Now let's say if you want to find out tau maximum for this cylindrical pressure vessel, then how can we find out? We know the equation of tau maximum for 2D loading condition that we have discussed in the chapter 7. That is sigma 1 minus sigma 2 by 2. Fine. And here sigma 1 is sigma H and sigma 2 is sigma L. So it is actually sigma H minus sigma L by 2. And we know that sigma H is equal to PD by 2T minus sigma L is PD by 4T divided by 2. So finally you will get PD by 8T. So this is the value of maximum shear stress in the pressure vessel. Fine. Now we are going to find strain in this body. Means actually we are going to find strain in cylindrical pressure vessel. Now first of all we will find strain in longitudinal direction. That is delta L divided by L. Fine. So if directly delta L is given, then you can use this equation. But if we know the stresses but we don't know delta L, then we have to use other equation, that is sigma L divided by E minus mu sigma H divided by E. Fine. That we have discussed in the chapter 2. And similarly, what will be the epsilon H? That is delta D divided by D, and that is equal to sigma H divided by E minus mu into sigma L divided by E. So actually this is the strain along longitudinal direction, and this is the strain along circumferential direction, and it is also strain along radial direction. Fine. Now here we know the value of sigma L and sigma H. That is sigma H is equal to PD by 2T and sigma L is equal to PD by 4T. So if you will put this value here, then you will get equation to find out sigma L. So it will be PD by 4TE into 1 minus 2 mu. And here this is the strain along longitudinal direction of cylindrical pressure vessel. And here if you will put hoop stress and longitudinal stress, then you will get PD by 4TE into 2 minus mu. And here this epsilon H is strain along radial direction, and it is also strain along circumferential direction, or we can say it is strain along tangential direction. Fine. So now we have strain along all the three directions. So we can find out epsilon V, that is volumetric strain in the pressure vessel, that is equal to delta V by V. And we know that volumetric strain is equal to strain in X direction plus strain in Y direction plus strain in Z direction. Epsilon X plus epsilon Y plus epsilon Z. And here we have three directions, that is direction along longitudinal direction, direction along radial direction, and direction along circumferential direction. So we can write that it is equal to 2 epsilon H plus epsilon L. Fine. And if you will put these values, then you will get epsilon V is equal to PD by 4T into 5 minus 4 mu, right? So that is the value of volumetric strain in the pressure vessel. So from here you can remember these three equation of epsilon L, epsilon H and epsilon V. And if you don't want to remember this, then you can derive as derived here. Fine. Now we will discuss that how to design cylindrical pressure vessel. Means we are going to find thickness of cylindrical pressure vessel. Now let's say in the question diameter is given, pressure is given, and permissible stress is given. So by using this value we have to find out thickness of cylindrical pressure vessel. So how can we find out? We know that stress induced in the body is equal to PD by 2T. That is actually hoop stress. And we know that in the case of cylindrical pressure vessel, hoop stress is greater than longitudinal stress. So we take induced stress is equal to hoop stress because it is maximum stress produced in the cylindrical pressure vessel. Fine. And for the safe design, we have to take sigma induced less than or equal to sigma permissible, right? Because if this induced stress is exceed permissible stress, then cylindrical pressure vessel will fail. So we have to take this sigma induced less than or equal to sigma permissible. And we know that sigma induced is equal to PD by 2T. So here we can write that PD by 2T should be less than or equal to sigma permissible. And now we have value of sigma permissible, pressure and diameter. So we can actually find thickness of pressure vessel. And from here we can write that thickness should be greater than or equal to PD by 2 sigma P. Fine. So if it is asked to find out value of thickness for cylindrical pressure vessel, then you can find out from this expression. And if in the question corrosion allowance is given to you, then you have to add corrosion allowance to this expression. Fine. And to find out thickness, take care in the units of these values. You have to take pressure in megapascal, diameter in mm, and stress in megapascal. So finally you will get thickness in mm. Fine. And you can also take all these values in SI unit. So finally you will get thickness in meter. But generally we prefer these units. Fine. Now let us understand that how to find pressure carrying capacity of cylindrical pressure vessel. Let's say in the question thickness is given, diameter is given, and sigma permissible is given. And we have to find out pressure carrying capacity of this cylindrical pressure vessel. So we know that for safe design, sigma induced should be less than or equal to sigma permissible. And in our case, sigma induced is equal to sigma h, that is hoop stress, that is equal to PD by 2T. Right? So here PD by 2T should be less than or equal to sigma P. And here we know sigma P, D and T. So we can find out pressure carrying capacity. We can write that P is less than or equal to 2 sigma P into T divided by diameter. Right? So from here we can find out maximum pressure carrying capacity, that is 2 sigma Pt divided by D. Fine. Now we are going to understand stress in spherical pressure vessel. Now we understand that in the case of cylindrical pressure vessel, we have three stresses, sigma L, sigma H and sigma R. And for thin cylindrical pressure vessel, it is negligible. Fine. Now in the case of spherical pressure vessel, we have pressure vessel having shape of sphere. So in this case, we will have two tangential direction and one radial direction. Here, this is going to be the radial direction, this is going to be the tangential direction, and there will be also one direction which is perpendicular to the screen at this point, and that is also called as tangential direction. Fine. So here if you will take any cube from the surface of this pressure vessel, then it will have this type of stresses. On radial direction it will have radial stress minus P, and on other two direction it will have circumferential stress, that is also called as hoop stress, that is sigma H. Fine. Means here we can also say that in this case value of hoop stress is equal to value of longitudinal stress. And we can find out value of hoop stress and longitudinal stress. For that you have to take this cross section of this pressure vessel. So it will be like this. Here in this direction we have hoop stress, or we can say longitudinal stress, and on this surface we have pressure. And we know that it is in equilibrium, so we will take sum of forces in vertical direction is equal to 0. So actually force by this pressure and force by this stress is equal. And here what will be the value of force by this pressure? That is pressure into area. And we also know that pressure on curved surface is taken as pressure force on projected area of this curved surface. So here we have to take area which is projected area by this curved surface, and that is going to be the area pi by 4 d square. So force by this pressure is pressure into pi by 4 d square. Now what will be the value of force by this stress? That will be sigma h into area, and in this case we have to take this area. Fine. So that is equal to 2 pi r into t. Fine. So here I can write means actually we are taking this area. And here this 2r is actually diameter. So we can also write it is pi d into t, means perimeter into thickness. So here we can write that it is equal to sigma h into pi d t. Here this pi is cancelled and one diameter will be cancelled. So we can write that sigma h is equal to p d by 4t. And this is the value of stress in this direction as well as in this direction. So in the case of spherical pressure vessel, value of longitudinal stress and value of hoop stress is same, that is equal to PD by 40. Fine. Now we understand that sigma h is equal to sigma L is equal to PD by 40. Now we are going to find strain in spherical pressure vessel, and we know that strain for spherical pressure vessel is equal to delta D by D, and it will be same in all the three directions, right? So here we can write that sigma h, that is strain in longitudinal direction, or we can say it is strain in tangential direction, or it is strain in radial direction. That will be equal to sigma h divided by E minus mu into sigma L divided by E, or we can also write that sigma h divided by E. Fine, because these both are same. And here if you will put value of sigma h, then you will get PD by 4TE into 1 minus mu. So this is the value of strain in all the three directions. And now we can also find volumetric strain, that is delta V divided by V. And we know that for sphere, delta V divided by V is equal to 3 into delta D divided by D. Means we can write that it is equal to 3 into epsilon H. Right? We know that epsilon V is equal to epsilon X plus epsilon Y plus epsilon Z. And for the spherical pressure vessel, we know that strain in all the three directions is epsilon H. So we can also write this epsilon V as 3 epsilon H. And we already know epsilon H, that is equal to PD by 4TE into 1 minus mu. So it will be 3PD by 4TE into bracket 1 minus mu. Fine. So here you can remember these two formulas. Now we are going to discuss that how to find thickness and pressure carrying capacity of spherical pressure vessel. We can follow same method to find out thickness and pressure carrying capacity as discussed for cylindrical pressure vessel. Fine. For the spherical pressure vessel, you have to take sigma induced is equal to hoop stress is equal to PD by 40. So it will be PD by 40 less than or equal to sigma P, that is permissible stress. So if you will find thickness, then it will be PD by 4 sigma P. And if corrosion allowance is given in the question, then you have to add here. Fine. So you have equation of thickness for spherical pressure vessel. And similarly from here you can find out pressure, and that will be pressure carrying capacity for spherical pressure vessel. Fine. So I hope that you understand how to find stress, strain, thickness and pressure carrying capacity for cylindrical pressure vessel and for spherical pressure vessel. From this chapter you have to remember some formulas, and by using that formulas you can easily solve any question from this chapter. Fine. And here our theory part of strength of material is completed. If I will find any new topic that should be covered in this subject, then I will make video on that later on. Fine. Now from the next video you will get previous year GATE questions of strength of material subject. Before going to solve GATE questions, make sure that you have remembered all the equations from strength of material. And you can also make one separate note of the equations of strength of material subject, and also read notes 3 to 4 times before solving GATE questions. So it will be easier for you to understand GATE questions. Fine? So today in this video we will stop here and we will meet in the next video. Till then, stay motivated and happy practicing.